I'd like to welcome all of you to the OSIRIS-REx mission to Asteroid Bennu, Curation, Celebrations, and Challenges. My name is Paige Graff. I'm the lead facilitator for today's session, but along with me, helping you out in the chat are Rosina Miller, Kim Willis, and Suzanne Foxworth. If you have questions, notice you'll want to have your chat settings to all panelists if you're on the live session so that Rosina, Kim, Suzanne, or perhaps myself can help address any of the needs that you may have. We're really looking forward to having all of you participate with us and our webinar speakers, Dr. Nicole Lunning, Dr. Christopher Snead, and Salvador Martinez. Now, I want to take a moment to welcome all of you. We have participants from a variety of grade levels, from down to third grade all the way up to college level, and educators. And you are all from 24 different states and 6 different countries. Here's just sort of a map that kind of represents where all of you are perhaps connecting with us from. So we welcome all of you, our live participants, as well as those of you who are watching the archive. Now, I want to take a special moment to welcome our speakers and again, our facilitators. We are here to help you. We're here to engage with you, and we are going to be asking you questions. Rather, I'm not, our speakers are. They're going to be asking you questions that we're going to want you to engage with us by providing some input to those questions in the chat. We're so glad to be joining from you. We are broadcasting from the NASA's Johnson Space Center in Houston, Texas. And as we get started, I'll again mention that we'll have 3 presentations from Nicole, who will talk about an introduction to the OSIRIS-REx mission and sample delivery or sample collection. Dr. Christopher Snead will talk about preparing and planning for the OSIRIS-REx delivery of samples. And Salvador Martinez will talk about an array of things, including the sample arrival, transport to JSC, and the power of engineers and processors working together. So we're so glad to have you joining us today. And before we launch into those presentations, we want to take a moment to have our speakers tell a little bit about themselves so you kind of have their background before they start sharing their content with you. So Nicole, or actually Salvador, let's start with you. Please tell us a little bit about yourself and your background.
Thank you, Paige. Yeah, so I am Salvador Martinez III. I am the lead Astromaterials curation engineer here in the Ares department. And I have done a lot of my recent work helping the OSIRIS-REx mission extract a sample from Asteroid Bennu. You can see here in this photo, there's actually a photo I like to show when I do these types of talks, is a career day photo of me as a 10-year-old. Back then is when I had my first, ideas of wanting to become an engineer. I'd always been very curious as to how things worked, and really having an understanding of, being able to transform something from just a raw material like a metal and transform it into a tool, transform it into a spacesuit. In our case, something that we could use to extract the asteroid sample. That process, it's always been something that I've been very passionate about. So in my career, I've done a lot of designs. I've helped on the new XEMU spacesuit for our return back to the moon, and as of late, been here in this department helping them extract the asteroid sample and work on any other astromaterials they bring back for collections.
Awesome. Well, thanks for your introduction. And let's move on to Christopher Snead to tell us a little bit about his background before we launch again into his presentation in a bit. Christopher?
Hi, my name is Christopher Snead. I am the Deputy Curator for NASA's OSIRIS-REx sample collection and the Curator for NASA's Hayabusa 2 sample collection. I went to college at the University of California at Berkeley, and then I went to graduate school at UCLA. It was at Berkeley that I participated in a summer research project that got me involved in this whole world of astromaterials curation. It was a comet sample return mission called Stardust, and I got to work on that very early in my career as an undergraduate, and it just kind of stuck. In my spare time for hobbies, I like to do stargazing. I've always loved astronomy. I also like building things with Lego, and I enjoy making leather things as well. And that's about it for me in a nutshell.
Awesome. So from our 10-year-old Salvador to our, UCLA and Stardust connections with Christopher, that's a little bit of their background. But last but not least, let's go to Nicole to tell us a little bit about her background. Nicole?
Hi, happy to be here. So I'm originally from Minnesota. I came to science and I'm a geologist, and that really started when I was in high school. I had a teacher that took us on trips to see the geology of the state all around me, and that's really when I got hooked on geology. I went and got both a bachelor's and a master's degree in geology before discovering that I could also combine my enthusiasm for space with geology when I started a job working at the Smithsonian Museum in Washington, D.C. and their division of meteorites. And from there, I really fell in love with meteorites and asteroids and decided to go back to school after working for a bit and get a PhD at the University of Tennessee. I was able to go on the co-led by NASA Antarctic Search for Meteorite expedition in 2019. And our field team found over 350 meteorites on the ice, which was an amazing, amazing experience. Shortly after that, I started my job here at NASA Johnson Space Center in 2020 and got to be part of the work preparing for the OSIRIS-REx samples to return. And then as we've now had them for a year and a half on Earth, our work curating, caring for them, studying for them, and characterizing them, which has just been absolutely amazing. And you'll get to see that in all of our presentations today. So thank you.
Awesome. Hearing that little bit of background about each of our speakers is one part of what we wanted to share, but I'm actually going to stop sharing my screen so that we can have Nicole, once I give her the ball here, we're going to have Nicole be able to share her introduction to OSIRIS-REx at Asteroid Bennu. So thank you, Nicole. I'm going to mute my camera for now so we can focus on you and what you have to share. So over to you.
Great. Thank you. So you all have heard us say the word OSIRIS-REx a bunch of times now. It's the name of the mission we're working on. It's an acronym. We love acronyms at NASA. And this is quite a meaty one. It stands for Origin, Spectral Interpretation, Resource Identification, Security, Regolith Explorer. Because this mission went to a near-Earth asteroid named Bennu. It was chosen because it's a near-Earth asteroid. That meant we could get there in less than a decade and bring a sample back. It was chosen because of its orbit. It's a relatively large near-Earth asteroid. And then it was, of those category, one of the few that was thought to be carbon-rich because it had a very low albedo. It's very dark in appearance from telescopes on the ground. So even though we show you relatively light images like this one of the asteroid, that's because that's a very high illumination. So the rocks that came from it are very, very black. And carbon here was a rough proxy, what everyone hoped at that time, for organic rich, because this mission is motivated by trying to understand the building blocks of life in our solar system. And I'll touch on that in a little bit of what's been found so far. But first, let's talk about how we got the samples. So this is an artist rendition of our amazing spacecraft, in which you can see that was sent to Bennu to collect samples. And I'm gonna ask you a question first. So I want you to check out this spacecraft a bit and think about what parts. We've added letters to 5 different parts, and look for one. What part collected dust and rocks from Bennu? What part actually collected the sample? And then the second question is, what part was the sample returned in? What we call a sample return capsule. So please put your answers in the chat and any details or ideas you have for the different parts you pick.
And for those of you perhaps watching the archive, you may pause the video so that you can come up with your own answers and then compare them to what is being put in our live session chat. And to answer that, we are getting a slew of answers coming in. And right off the bat, we have Clark Planetarium saying E for the sample collected from, and I lost their answer, and D for the what they were returned in. Grand Valley State University, they are saying 1 is E. And then from Irvine, we have 1E and 2D. And then for Solar System Ambassador from New York, they're saying that for number 1, the answer is D for the collection of the samples. Our Solar System Ambassador from Florida says the answer for number 1, they think, is C. One of our science engagement folks is indicating that the rocks were collected using letter E, and they were returned and delivered to Earth using letter A. So we've got a variety of answers. Randall Middle says E, perhaps for number 1. Our Solar System Ambassador from Florida says for number 2, D. So we've got a variety of answers. Spartanburg County Public Library says E for collection and A for return to Earth. And let's see what else we have here. Duxbury Senior Center says for number 1, D. And let's see, we have a Solar System Ambassador from Indiana. They say for the collection, E. For the return to Earth, A. And we actually also have someone from Florida, from the Kennedy Space Center area, and they're saying E and D for the collection of the samples and for the rocks to be returned. And so let's see, spacecraft knowledge, help us understand, Nicole, what was what here?
All right, so here I'm going to the slide with the answers you can see. So for the first answer, the part that collected the samples, it's E. That's the touch and go sample acquisition mechanism, or tag SAM head. And it's on the end of an arm that actually, when the spacecraft was flying to Bennu, was folded in and then could extend when we were getting ready to collect the sample. For the second question, the sample return capsule is D. For those of you who guessed A, I can understand why. It's a very similar shape. That's actually our high gain antenna for communications back and forth with Earth. And you can see C has a bunch of the camera systems for observing the asteroid, both as the sample was collected and during extensive mapping that happened before the samples. And I don't think anyone said B, but B are the solar panels. So you can see here, and I'll show you some videos later of both the sampler head and the sample return capsule. You can kind of see on this image how that sampler head was then put into the sample return capsule and detached from the arm it's on. But first, we'll show you this small movie of how that sampler head works. So it actually uses nitrogen gas to pull sample inside. So it basically what we call entrains, or gets a bunch of dust and rocks in the gas, and then uses that to bring it into the sampler head. So, and we then, as you'll hear from Christopher and Sal, took this sampler head apart to get at that sample. So one of the big surprises when we got to Bennu was it was covered in these massive boulders. Here you can see in the black and white image, which is taken by the spacecraft at Bennu. Some of these boulders were as large as 50 feet, absolutely giant. And this sampler head is a little over a foot. It's about 13 inches in diameter. And so you can see this maybe changed our plans a little bit. This sampler head really was designed to take in more like sand particles. If you think about, you go to a beach, either a lake or near the ocean, more things of that size, or small rocks and pebbles, where these huge boulders, the sampler head was not designed for this. So our next question is, how do you think this affected our plan to collect samples using this touch and go sample acquisition mechanism, or tag SAM? Please put your thoughts in the chat.
So again, let's think about this. And for those of you watching the archive, you may want to pause and then see what the answers from your learners may be. For those of you with us live today, we're very interested to think about how you think these large boulders affected the plan to collect samples using TAGSAM. So our solar system ambassador from Indiana says perhaps it caused a change in the collection site. Another individual from Duxbury Senior Center mentioned maybe you had to find a flat spot to make the collection. Another individual said challenging to find the spot to approach using the TAGSAM, so you had to really look hard to find one. Center for Science Engagement said perhaps you needed to locate a place on Bennu that had the smallest possible rocks. Another individual said perhaps you needed to reassess the locations for sample collection. Someone else is mentioning that I think they had to back off for a year to scan and observe the big rocks and make some decisions. Someone else from our solar system ambassador from New York is mentioning maybe you needed to aim for dust and find where that might have been located on the surface of Bennu. So it looks like we're hearing finding maybe a flat spot or even perhaps a delay. What do you think, Nicole?
Yeah, so they absolutely caught on to a whole bunch of the facets that the sample collection place decision all of a sudden needed to be focused on what we could sample. We, had thought it would just be, oh, you could pick anywhere, and so pick the favorite spot. And now it was much more, what can we pick? And that was narrowed down to 4 sites that were mostly recent craters with, as people said, fine grained, smaller rock particles that actually could be pulled into this sampler head. And there's one additional thing that also had to be added is they actually wrote additional programming. This is called natural feature tracking, and this was not part of the original sample collection plan. So at this point, our communications delay between Earth and the spacecraft was over 18 minutes. So you could not have somebody driving and maneuvering the spacecraft to avoid rocks. And they didn't know that this would be a problem. They expected Bennu to be more like some other asteroids we'd seen, where there's huge sort of almost what they would call ponds of small material. And since Bennu didn't have that, and they needed to develop a system where the spacecraft itself could drive away from rocks or nudge its landing trajectory so it wouldn't hit a rock, or if it was getting close, it would actually back off. We ended up not needing to use that feature, but it had it in case the spacecraft was not able to maneuver itself, so the TAGSAM head would touch an area that wouldn't have big boulders on it, as you can see here. So here I'll show you a video of, this is the actual TAGSAM head approaching the surface of Bennu. This is sped up a little bit with images, but the images that were also being used by that natural feature tracking system. And so this is about the 5 minutes approaching the asteroid, and then the sample collection was only about 6 seconds to bring samples in. That arm actually sunk in to the asteroid by almost half a meter, which is pretty incredible. And then when it came out, it was so full of material that there was sample leaking out of it. And that's actually because there were larger particles than were expected to be able to brought into the sampler head, actually holding open a flap, what we call the mylar flap. And so a decision was made to pretty rapidly stow it. This meant actually skipping a planned mass measurement because we didn't want to do an extra mass measurement, but then lose all the mass of the sample because it was actively leaking out. So here you can actually see on the bottom that TAGSAM head being stowed into the sample return capsule. So it opened, the sample return capsule opened to receive the TAGSAM head, and then closed until we got it back to Earth and it landed in Utah, as you'll hear about from Sal pretty soon. So I'm just going to wrap up my section of this presentation, circling back to those big questions of this mission of looking for the building blocks of life in our solar system. And so we've had this sample on Earth about 1.5 years. And just this last month, we had these amazing papers from our team come out discovering all sorts of different components of the building blocks of life in these samples that could only be discovered because of the rigorous, careful contamination control, knowledge, and prevention of earth materials getting into these samples, so that we can really have a very high degree of confidence that these compounds are from Bennu itself, both really unique evaporite minerals that are very environmentally sensitive and easily lost if exposed to Earth's atmosphere, really interesting ammonia with heavy nitrogen isotopic compositions that strongly indicates that Bennu's original parent body probably formed farther out of our solar system than Jupiter is. And a wide array of organic compounds. All 5 of the nucleobases are building blocks for DNA and RNA for life, and 14 of the 20 amino acids that life as we know it uses to build proteins. So really exciting findings so far. And with that, I'm going to hand off to Christopher, who's going to really help you understand how we got there, how we prepared and rehearsed to take hardware apart and to care for this sample in clean rooms.
Okay, so I'm Christopher, as I mentioned before. One of the things that we had to think about a lot during the OSIRIS-REx mission is how we were going to process the samples very carefully once they returned. So the mission itself, the spacecraft itself, had this long journey from Earth to the asteroid and back. It was about 7 years. We on Earth had a similar journey getting ready for what we were going to do with these samples, how we were going to protect them, how we were going to categorize them and measure them, how we were going to photograph them, and ultimately send them to scientists for analysis. This is what we do in Astromaterials Curation. One of the tools that we used very early on was computer-aided design to understand where equipment and tools would go in our sample processing labs. We also had to think about when the spacecraft returned in the Utah desert, how we were going to care for it, make sure that we disassembled it appropriately and prepared it for its journey back to Houston. So CAD was a very important tool we used. We made a lot of the equipment in virtual models, and we were able to lay out and plan and see what made sense. Let's see. So let's think about rust for a little bit. One question that we have to address is, why do metal things, especially metal things with iron, rust? And really, the main thing that causes rust is oxygen in our atmosphere. We also have water in our atmosphere that accelerates this process of oxidation. So a question that I have for everybody in the chat is, if samples from asteroid Bennu contain iron, how would we keep them from rusting?
So for those of you again watching the archive, perhaps think about this, stop your recording and see what kind of answers your learners may come up with. For those of you on the line, let's see what you're thinking in terms of how we would keep these samples from rusting. So our solar system ambassador from New York says no oxygen. Center for Science Engagement says place them in an airtight container. We'll see if there are other responses. One from Randall Middle School says perhaps a closed container with nitrogen. Duxbury Senior Center mentions to keep them in a vacuum. One of our other individuals is mentioning to put them in a clean room. Someone else is mentioning to fill whatever container you're working in with an inert gas. So it looks like we've got some individuals, Christopher, that have some very useful thoughts. Even someone else from the Kennedy Space Center area is mentioning to keep those samples in a vacuum. So what do you think, Christopher? How does this all work?
So all of those answers are very good answers, actually. And what we do, in fact, is we keep them in nitrogen purged glove boxes. This is our primary way that we keep our samples protected from oxidation. We purge it with pure nitrogen gas. So in case you don't know, our atmosphere is mostly nitrogen gas, but there's about 21% oxygen and a little bit of other gases like water and other things. So we purge these with very pure nitrogen gas, no oxygen, no water, and we can measure that in real time. This protects the samples from changes in the composition due to oxygen and the water from the Earth's atmosphere. So I mentioned metal because that's an oxidation that we're very familiar with. But there are all sorts of other minerals in the asteroid samples that react very easily and quickly with terrestrial water and oxygen. And we want to make sure those wonderful results that Nicole had mentioned in the previous talk are really from the asteroid and not from contamination from Earth. We also keep these glove boxes very clean and sterile, so samples can't be contaminated from Earth dirt or from bacteria, which may want to eat some of the asteroid organic material. And the sample processors have to do all the things that you'd think about doing, taking apart hardware, handling tiny rocks and pebbles, weighing and photographing the samples. All of this has to happen inside of these glove boxes. So another question we have is, how do you think the team prepared to work with these samples from Asteroid Bennu? And we have some options here. We practice using glove boxes in the lunar curation lab, or the moon rock curation lab. We built model glove boxes and practiced working inside them. We used Lego to create and practice equipment and glove boxes. So think about what your answers would be to how we practiced.
And as you do put those answers and input into the chat, perhaps you can give some reasoning as to why this or why that. Not just a letter, although a letter is good, but if you think about the why you think this could be a potential answer. So one of our groups, Palm Springs North Elementary, is thinking C, using Lego. An individual from the Kennedy Space Center area is thinking maybe a practice in the Moon Rock Lab. One of our solar system ambassadors from New York thinks you probably did a little bit of all of those, so all of the above. One of our solar system ambassadors from Indiana is thinking maybe both A and B, and possibly C, because that might have been a less expensive cost. Our Clark Planetarium group is mentioning that, practice does make perfect, so you're definitely important to practice. Randall Middle School, which is a group of 6th graders from Florida, they're saying a letter B. You built model glove boxes to be able to practice before you actually worked with the actual sample. So we've got a lot of practice does make perfect, and some thoughts on maybe you used other glove boxes or perhaps Legos. Christopher, tell us what you actually had to do.
So those are very interesting answers. The answer is mostly B. There was a little bit of A, but for the majority of our practice, we used glove box mock-ups, which are full-scale models of the glove boxes. Since we expected the collected asteroid samples to be smaller than the moon rocks and the meteorites we usually curate, we actually had to design new glove boxes to improve the sample handling and photography. We also had this new activity where we had to take apart the TAGSAM, that mechanism that collected the sample that Nicole had showed. We had to disassemble that to get to the asteroid regolith, and that had to be done in the glove box. So to practice this, we built mock-ups, and these are very useful for understanding how comfortable working with samples would be, the ergonomics of it so that we don't get cramps when we're working, and how hard or easy it would be to handle tools. And this is useful because we don't want to commit to having a full glove box made from metal, which is very expensive. And we can test our workflows with most of these we made out of poster board or we made them out of plywood and 80-20 stainless steel, or 80-20 aluminum. So we did frequent sample handling and tag SAM disassembly rehearsals inside of these mock-ups. So this did a number of things. It helped us develop the practices, what techniques were best to divide the sample. The processors developed muscle memory, so when it came time to work on the real samples, they'd been so familiar with these actions that it was second nature to them. And also the familiarity with working with team members. You see in one of these pictures, there are 4 different individuals kind of working in tandem to handle the samples. And this is very important to practice that kind of coordination. We also had to practice taking pictures of asteroid samples, which we expected were going to be very dark. And we had to take those through our glove box windows. So our photography and our engineering team developed special equipment and techniques to overcome this challenging problem. So that was a thing we also had to practice a great deal. And our last practice that we did before the samples returned, I'd like to call it a dress rehearsal, because we did these in the actual finished glove boxes just a few months before OSIRIS-REx returned. And that's the picture you see on the lower left corner, is us practicing with simulated materials that were clean and wouldn't contaminate the glove box, but in the actual glove box. So one final thing we had to practice was that in addition to the main method of collecting samples, which Nicole had talked about, there were also these special metal Velcro contact pads that were placed around the tag SAM to collect the particles that were at the very top of the asteroid surface. These surface particles on this get irradiated by cosmic rays and solar wind. They also get hit by micrometeorites. We call these processes in general space weathering, and this can affect the spectral color of the asteroid. So a lot of the observations we make of asteroid are made on Earth, and we use radar, and we can understand something about the spectrum of these asteroids if we understand how this weathering affects the color. These particles are very small, and they're difficult to remove from Velcro. So one of the things we had to practice were picking these particles out. Doing this by hand with tweezers is very difficult to do, very, very challenging. So we developed a device that allows a sample processor to grab these tiny particles using a series of knobs. It's kind of like a miniature claw machine that you would use in an arcade. And we practiced using asteroid simulant. This is basically just a very dark volcanic rock that we used. And the first particles that we actually picked from the OSIRIS-REx contact pads were done using this same device. So these are some of the ways, and not all, but some of the ways in which we practiced getting ready for the samples once they returned. And now I'm going to hand it over to Salvador to tell you a little bit about the experience of being in Utah and preparing using engineering and working with processors.
Thank you, Christopher. Okay, well, hi everybody. Thank you for joining us. As I introduced myself a little while ago, I'm the lead Astromaterials Curation engineer. I'm going to talk to you right now about sample arrival and transport to Johnson Space Center. So I'm actually going to go back one slide to see if I can show you guys. One thing that's I think is one of the cooler sites here is when the capsule came back to us, September 24th, 2023, the spacecraft didn't actually touch down onto the Earth. It actually just flew by and it released the capsule down towards us. So we have a rendering here on the left-hand side, but on the right-hand side is actual photo from the spacecraft. And you can see there almost like a crescent Earth on the left-hand side, some of the sun rays up on the top, and then of course the capsule. And so this is where we began to actually have our sample arrive here at Earth. So it entered into our atmosphere and it landed down in the Utah training and test and training range where we had our sample return team. A lot of our JSC curation team members were out there having multiple rolls depending on the sample coming back in different configurations, where it landed, if it was nominal conditions, off nominal. But for our sake, luckily it landed perfectly down onto the desert, and we really immediately got into basically the best case scenario is team members were able to access it, observe that the capsule was everything was intact, everything was great, placed it onto a cargo net and attached it to a helicopter. And our helicopter then transported it to our portable clean room. And our portable clean room is where our actual Astromaterial curation team was ready to start disassembly and the beginning of actually us extracting the asteroid sample. And you can see here on the left-hand side, this is our portable clean room. And we have our team members on the right-hand side shown bringing in the actual capsule. And so the parachute had been removed at this point and is getting ready to be brought in to our highly clean clean room and begin to remove the actual back shell and the heat shield. Very intensive processes. And I think on this next slide here, you'll actually see myself, Christopher, and I think Nicole are in some of these photos. But this is us in the beginning of the removal process of the heat shield and the back shell. Took several hours of diligent work, a lot of members around, all in different roles. I think I was doing documentation at this point, along with Christopher. Nicole was actually inside of this portable clean room, helping to identify all the components that needed to be removed for the heat shield, the back shell, and facilitating everything. I think all in all, it took us a better part of almost 10 to 12 hours to basically bring in the capsule and start to actually remove the back shell heat shield and connect it into what we're calling the nitrogen purge. So once we got we got out of this the heat shield and back shell, we had to then think about how are we going to transport it back to the Johnson Space Center, to our clean rooms, to our labs. So here's our question, or my question for you. How do you think the capsule was transported back to Johnson Space Center? Do you think A, we took the entire clean room? Yes, it doesn't seem very big. Maybe we loaded it all back into a truck and drove it from Utah to Texas. B, we checked it into luggage on a commercial airline flight and brought it back to Houston. Or C, other. Any ideas of how you think we would get this capsule with asteroid sample back safely into our clean room labs here in Johnson Space Center?
So a very interesting question that we'd love to see if you have thoughts and ideas and considerations of what they had to take into account. So right off the bat, Center for Science Engagement says you put it on a large bed of a truck, letter A. Another one of our individuals said maybe you put it on a commercial airline because it's, perhaps a bit cheaper. A solar system ambassador from New York is mentioning probably on the large bed of a truck, as does Palm Springs North Elementary agrees, the large bed of a truck. Yolo County Library also thinks probably the clean room was portable, so you put it on the back of a truck. Someone else is indicating maybe an Air Force plane. Someone else has indicated probably not B, but maybe some other type of plane like a military cargo plane. One of our individuals from the Kennedy Space Center area says maybe the large bed of a truck. Clark Planetarium says probably something else, but we'd be interested to know, Clark Planetarium, what is that other something else? Someone else has mentioned transport it to the destination as quickly as possible, but they're not quite sure how. Randall Middle School thinks, maybe a large bed of a truck is how this was transported. And Duxbury Senior Center says maybe a NASA jet. So I don't know. I've not been on one of those NASA jets, but I'd like to be on one. But is it a NASA jet, a commercial airline, a truck? Salvador, how did we get it transported to the Johnson Space Center?
Okay, all great answers. Thank you all for participating. And the actual method was a C-17 Globemaster aircraft. It would fit in. Honestly, getting it back as quickly as possible was a priority. So even though it's not out of the realm of possibility to transport this thing in a vehicle, putting it on an aircraft and flying a few hours was definitely the fastest way. So we took the capsule once it was ready to be hooked up on OPERGE into this transport box. And our entire sample return team, not just here at Johnson Space Center, but Lockheed Martin, everyone, Mission Center folks, from Goddard, from University of Arizona, all of us got to ride into the C-17 and go back to Johnson Space Center. And one of the cooler photos of our actual flight is actually this one here, which is us leaving the Utah desert range. So ride of a lifetime for sure. It was a very, I'm sure Christopher and Nicole would agree, is a very eventful ride, very exciting time for all of us. But as soon as we got back, that's where the work actually started for our curation team. So once the capsule arrived, we began to bring it into our glove boxes. And Christopher he touched on this a little bit, where we want to work in these clean labs. We want to protect the sample. We want to make sure we keep the sample pristine for all the science that wants to be done on it. So when we come to how do we bring things into a lab, how do we extract the sample safely, it's a rarely complicated answer. This mechanism, the tag SAM, it has so many features that we had to remove. We had to practice. We had to develop new tools. We had to invent new methods. All this thing in basically this new era of curation, where we're working hand in hand with processors and engineers to develop all these tools and equipment. So what you're seeing here is that we're starting to really open this canister, and we see the mechanism. You can see this dark, it looks almost like coal. That's all the asteroid sample that was waiting for us the moment we started to open it. And so a lot of surprises on the way, starting with just immediately opening the capsule. But when it comes to how we actually did the work, there was a lot of preparation, a lot of tools, and a lot of actual interfacing with both processors that are being the ones that actually handle the Astromaterials sample, and the engineering team who's developing a lot of the tools that they use to actually process the sample. So, question for you is, how long do you think our OSIRIS-REx team of processors and engineers practiced to be ready, to be prepared for this disassembly of the tag SAM? And I want just a couple of different formats here in time. So days, if your answer is in weeks, in months, or in years. Please put your answers in the chat.
All right, so let's think about this. How long do you think, and how, give us a quantity as a part of your answer. So Grand Valley State University, they think this probably took years and perhaps even up to 7. One of our solar system ambassadors from New York says probably months, but we want to know how many you think. Another individual thinks 5 to 6 months. Someone else has indicated probably more than 2 years. Clark Planetarium says perhaps it started, once the spacecraft actually launched. Our solar system ambassador from Indiana says months, probably maybe a year or more, perhaps. Palm Springs North Elementary says probably years. Our solar system ambassador from New York is thinking at least 6 months. And they're all putting little question marks in there as, that's kind of what we're thinking, but we're not sure. Our individual near the Kennedy Space Center says probably about 2 years. Center for Science Engagement says, I would think at least a year. So practicing, I don't know, we've got a range. No one thinks it's days or weeks. It's either months or years. So Salvador, how long did you all work on this to practice for disassembly?
All great answers. Yes, because there were so many different steps and so many tools and so many members of the team, the answer was never going to be days or weeks, even months. That would take a lot of months. So at least for the time that I've been here in this department, I think the answer is it's at least over 18 months. So about a year and a half of my direct involvement. And honestly, there had been people before me that were still working on how are we going to curate the sample from the time that it launched and from really the beginning of this mission or beforehand. So it is in years. And at least in my involvement, almost 2 years. And Nicole and Christopher had been involved before I was, so their answer is probably a little bit different in perspective, but a lot of work and a lot of time. And when it comes to seeing how exactly we were able to develop these things, I do go back to kind of what Christopher touched on, the mock-ups. We needed to practice, because you don't get to this final image here on the left-hand side without first preparing yourself with the image on the right-hand side, where we have, some wood, some aluminum, some prototypes to prepare yourself for when the actual sample comes back, when you have the actual asteroid regolith, you have everything that you need to do this safely and efficiently, in the best way possible. And so, yeah, 18 months, there it is, year and a half. So over the course of the time, we were in rehearsals repeatedly. We were developing new tools, we were inventing new methods. You can see here our team is highly varied, different skill sets. So we had to identify what processes worked for which people, what teams were working on these things, and then what equipment that they need. And how do we then verify this is the right equipment? Do we need to make changes? And so our engineering team and our processing team worked hand in hand very intensely to make sure that when the sample did come back, we were prepared. And even then, there are some challenges along the way, but that is what you can do to prepare yourself for something of this complexity, of this magnitude. And as we're developing it on the engineering side, you can start to see, we have our models, Christopher touched on this as well, where we do things virtually. We get to see and create these parts in a three-dimensional space, in CAD space, and verify and check and optimize and do a lot of different reviews and optimizations and iterations. And in this process, it's almost like we're carving out of a marble. We're slowly chipping away at parts that don't work, at things that don't work. And at the end of it, we have this really unique piece, and it's meant for one purpose only, and that is to help us get to the sample being extracted. And you can see here on the left-hand side, we have a lot of our prototype tools in the mock-up and all the practice and preparation it took us to get there. And on the right-hand side, the final version of the sample in the trays. You see the sample made it into the trays safely. You see the trays where they were out of foam at one point. Do what we can with prototypes, test things, and then you see the actual final versions. But even when it comes to preparing like we did, there's always going to be challenges, and there's always going to be things you cannot account for. This is a very difficult industry to work into. There's always a new insurmountable challenge, it feels like. But in the moments where we needed our team to come together the most, we did. And that's one of the big messages that I like to touch on when we talk about the processors and the engineering team is, our team worked together so well. We overcame so many of the challenges because we had worked together so closely. We developed all these new ways, new methods, new tools. And in the grand scheme of things, we were able to extract the sample in a safe way and facilitate it being sent out into science, and great discoveries are being made from it. It's one of the significant accomplishments of my career, and honestly, it's one of the more incredible moments that it's hard to put into words. But for us, teamwork did make it all work. It was extremely challenging, as Christopher and Nicole will touch on, I'm sure, in the questions, but that's what's great about working here. And here is our entire OSIRIS-REx Curation team. You can see on the left-hand side here, and I've got Christopher, myself, and Nicole pointed out. And on the photo on the right is when we successfully removed the stuck fasteners with our team and the tool that I invented to help remove that. So all in all, wonderful experience and a great team.
Awesome. Well, thank you, Salvador, Christopher, and Nicole for sharing these bits of information about the OSIRIS-REx mission and how we collected the sample, all the preparation and planning, even using of CAD design and in the glove boxes to have the sample once it was delivered, and then the fascinating aspects of getting that sample in Utah, getting it transported to the Johnson Space Center, and then the power of working together as a team to overcome any challenges and to celebrate this amazing treasure trove of information to help us better understand the history and evolution of our solar system. So thank you so much. Now, before we go into some Q&A, and I think there are some questions, and feel free to put your questions in that Q&A area, and we'll get to them as many of them as possible. But I just want to give our speakers a moment to sort of reflect upon themselves as perhaps as a sixth grade student, we have sixth grade students on the line and some of varying grade levels, high school, college level and on. But I want them to perhaps share a moment of reflection of if you were going to give advice to yourself from when your younger days were, what might that advice and thought set be to reflect upon? So let's start with Salvador. What kind of advice or reflections would you like to share with our participants?
Great question. I still have a lot of memories of me being in that age, when I was young in that career day, and I'd felt like there was something in me that was calling me towards being an engineer. And it may seem kind of naive to think a 10-year-old can feel that or perceive that, but if you've been watching this presentation that we had, or Christopher or Nicole presented, and something in that sparks a fire in you and has you feeling like your dream could be tied into something that you want to do, if you want to be here helping us in astromaterial curation or whatever it might be, if you feel that fire, go after it. Because as a 10-year-old, you probably never imagined you could even get to somewhere like this. I know I didn't, at least. So I appreciate it a lot. But if I had never gone after it, I wouldn't be here. So please, if you feel that fire, chase it and you'll achieve it.
Great advice. How about you, Christopher? What would be your advice for your younger self or for any of the folks on the line out there?
So my advice to my younger self would be, don't forget to play. Having hobbies and interests and activities that don't seem to have any immediately useful purpose. That's an extremely important thing, because often those activities turn into advantages and skills that apply to your future job in ways you'd never have imagined. So make sure that you give yourself time to play and pursue esoteric, fun, silly interests.
That's really great advice, to find that play that becomes work, but the importance of the skills that you build along the way is so important. Thank you, Christopher. How about you, Nicole? What is your sort of advice for your younger self or for those on the line?
Thanks, Paige. I think I would tell myself to really practice doing things that are hard for you. That it's something that I feel like I learned a little bit when I was a bit older than that, where you see folks like us and it looks like, we naturally knew how to do everything and went at it. But I think for every single one of us, there was lots of things that we came across that we didn't know how to do. And then we had to get somebody to teach us or figure out on our own. And most people who get to do the kinds of things we do didn't naturally, weren't born being able to do those things, or they weren't easy for them the whole time. And I think to not be discouraged when things are hard, and even just to practice doing things that are hard, making yourself do some things you're not good at, that can be a really valuable thing for me, both in, as Christopher kind of talked about, in play and things like that are fun, that practicing doing things that you have fun doing but aren't good at, as well as just developing that skill that really can help you have resilience to get through the tough times, and the difficult hurdles to figure out and problems to solve.
Absolutely awesome, Nicole. Hard things are important things to experience, because as you overcome those challenges, you learn the value and you get to celebrate all that you've learned along the way. So thank you, Nicole, Christopher, and Salvador, for sharing those aspects associated with pieces of advice you'd give yourself or those on the line. So now maybe, Salvador, if you stop sharing the presentation, we can perhaps have a focus on our speakers, because I see some questions coming in. I have some questions that came in earlier as folks were registering for the webinar. And so I want to take a moment to go through as many questions as we can. And one thing that I'll note is we are close to the top of the hour. So for those of you that perhaps need to depart to move on to another class or to move on to something else that is on your schedule, we thank you all for your participation, but we're going to stay on the line for an additional 15 minutes to get in as many questions as we can. So here's our first question, and I'll have this question. I think this is one for Nicole, and this came from a University of Montana group, and they're wondering, you talked about your experience with the Antarctic meteorites and searching for meteorites. So how do discoveries or potential discoveries from studying samples from Bennu relate to meteorites, or do they?
They do, and a bunch of the questions that motivated this mission, the foundational evidence that we really, stand on the shoulders of, came from meteorites. That most meteorites came from our solar system's asteroid belt, just like Bennu came from our solar system's asteroid belt, at least most recently. And so to even formulate the questions that a near-Earth asteroid like Bennu, a potentially carbon-rich asteroid that we now know it to be, might have organic compounds and the building blocks of life, those were only made possible by studies of meteorites. But one of the things then that being able to study Bennu samples, where we've had all this work, where the controlled custody that Salvador showed you that we did from landing to get it to Johnson Space Center, the handling in glove boxes that both Sal and Christopher showed you, all of that made it possible for us to learn things that we hadn't been able to learn from meteorites before, because all meteorites have passed through our planet's atmosphere, landed on the ground, which is a potential contamination vector. And so sometimes we just can't, with meteorites, eliminate that contamination possibility. And one of the things that has been a really kind of unsung discovery so far of the mission is the discovery of all 5 of the nucleobases for DNA and RNA. So those of you who, I'll actually very quickly share a slide showing this. Just quickly, for those of you, I know lots of different backgrounds here, but some of you, this is a refresher of your high school or maybe even junior high biology. Some of you, it's to come. These 5 compounds that are foundational to all DNA and RNA as we know it were found in the Bennu samples. They'd been previously found in a meteorite sample called Murchison, but that landed in Australia in a place where a lot of cattle or cows grazed. And so you can imagine it was hard to be completely confident that some of these compounds from terrestrial life hadn't gotten into the meteorites. And now we know from the Bennu samples that all of these compounds that are needed to form DNA and RNA are actually out there in solar system bodies that obviously could have been delivered to Earth, early Earth, or other places in the solar system. So
fantastic. And thank you for sharing that and for sharing that slide. And that was a great question from our University of Montana group. Well, here's another question, then maybe we'll go to Christopher and or Sal. One of our individuals from Huntsville, Alabama, and we had another individual online ask, does the asteroid sample have any kind of smell to it? So Christopher, maybe we'll start with you, and Sal, if you have any additional comments, we'll see what you have to say.
So the answer to that is yes. And it was something that we were able to experience in the cleaning of some of our equipment that was no longer going to be used in the glove box. And I actually wrote down my impressions of the description of the smell when I first smelled it, because it's a very otherworldly smell, but familiar in certain ways. So my first instinct was to describe it as smelling brown, which doesn't make a lot of sense. But then there was a hint of sulfur, like right after you strike a match, a hint of a circuit board working too hard, like in your computer, and then a hint of decomposing forest. And all of it had a slight sweetness on top of it. So I know that's a very strange description, but that's pretty much how I experienced that.
Fascinating. Salvador, do you have anything to add to that?
I mean, Christopher did a great job describing it. And that is a SparkNotes version of what he actually wrote down. It was very lengthy, very detailed. But I agree with him. It overheating electronics, like your laptop, when it gets a little bit too hot on your lap and you've got to pick it. There's a little bit of that, and then I got the sweetness came through as almost like maple syrup. So if you're eating breakfast and your laptop's to overheat, and then you knock them both together, and there's a little metallic sweet. It's otherworldly and hard to describe, but yeah, it was one experience. I don't think I'll ever forget that scent. I wouldn't say it smells like the color brown, but I don't know what else to say to describe it. So let's just go with that. Let's go with that.
Well, and it's interesting to think that, Christopher, you actually made a list of your observations when you first um, uh, sensed them. And, you know, for the individuals out there, writing and logging observations as they occur to be able to then reflect and go back to that moment in time that you may or may not remember with that kind of specificity is so important. So, Christopher, that is just so fascinating, your interpretation and your logging of those senses. So great question, and thank you for your responses. And Nicole, if you want to throw anything in there, let us know.
Oh, I think they covered it well, but it is a very unique otherworldly smell.
Excellent. Well, here's another question that we got from Palm Springs North Elementary. Now, Nicole, you mentioned that there was a process to kind of identify Bennu as a target of interest, but how did they actually even go about identifying and finding that Bennu was this location to be able to collect a sample from? Can you talk about that a little bit?
So it was using asteroid surveys that NASA is part of, also other international agencies supporting observations via mostly ground-based telescopes, but also some additional. Bennu is a size where we really do have to carefully look for, but our ability to see asteroids, even Bennu is a little under 500 meters across in its equator diameter. So that survey has really increased just in my lifetime in the last couple decades, from us only really knowing a few thousand asteroids to knowing hundreds of thousands of asteroids in our solar system, from both just their light features, and then as they narrowed them down, having more telescopes look at them and observe different what we call spectroscopic features to really pin down that this was a dark asteroid and a good candidate.
Excellent. Great question from our students out there. Now, here's another question. A couple of individuals, I think this one is for Sal. And so a couple of folks have mentioned, can you please discuss and share the challenges that you had with opening the sample compartment? What was the problem? How did you solve it? What kind of brainstorming and troubleshooting took place? And another individual mentioned, yeah, what caused the stuck fastener?
Yeah, very good question. We don't really have an answer yet for what caused the stuck fastener. This mission was spanned years in space, and so there's a lot of challenges when it comes to just doing things normally in space, much less over a period of time touching down to an asteroid and returning back to us in the clean room lab. So it'll take some time, I think, to really get to what caused it. But we know that when we rehearsed, when we practiced, we were applying a certain torque in the clean room. When we applied that, those screws were not moving. So the challenge, and I guess the brainstorming once we get to something like that is, well, we need to be able to increase the amount of force and torque we can apply, but we also need to do it in a way that is really easy to do inside of a glove box, which we maybe didn't cover as much, but working inside of a glove box is extremely challenging. There's a lot of restrictions with space, ergonomics, and also, the constraints of working in that area. It's fatiguing. It poses a really unique design challenge. So doing something in there to the amount of force we needed to apply, and then to do it safely so that we don't endanger potentially damaging the screw or really putting any of the force into the mechanisms or the sensitive equipment in the glove box. So adding another layer on top of already challenging, increasing the torque, doing it safely, doing it in a way that is simple. And then we had, I think, about 6 weeks to manufacture, test, approve, and then attempt to remove the screws. And so brainstorming was hectic, but it's one of those things where our team banded together, and everyone across the board contributed so much during those times to make sure that when we had our chance to take them off, that we would, and we did, and here we are. So teamwork.
Another thing I wanted to mention that I don't know if we touched on in too much detail in the talk. One of the things we're worried about when we get samples back is understanding its chemical and its isotopic composition. So we're very, very careful about what metals and what other materials we introduce into the glove box. So we can't just take a screwdriver bit that we get from Home Depot and introduce it into the glove box. There are a very limited number of tools that we have to use and materials to address a problem like that. So on top of what the engineering team had to accomplish just in terms of the mechanics of opening it, they had to do it with a very restricted list of metals and materials they could use. So that's an additional challenge.
And that's a great additional point to make. And as I think someone famous out there said, failure is not an option. And where there's a will, there's a way. And teamwork really makes it all happen. So great question and great answers and input from both of you. Now, maybe this is a question for Nicole from the Center for Science Engagement. They're wondering, how did they test the TAG-SAM on Earth and how it would actually collect materials at the surface of Bennu?
So they did actually a number of different things. They had a test bed set up by the spacecraft was made by Lockheed Martin, and they had a test bed with basically chips of, I think first they used a type of basalt, and then they used a tagish-like meteorite analog, so not actual meteorite, but material that was made to be an analog, and practiced the maneuver of pulling it in. But they did do one parabolic flight where they simulated the very low gravity conditions for the TAG-SAM as well, to confirm the basic functionality of it as well. So it was extensively tested all before assembly. And the one that we did a lot of our practicing on disassembly, the TAG-SAM, was actually what they call the qual head, or the qualification head, that was used for a lot of that testing, because the one that launched and went to space went through a ton of cleaning and was made specifically for that, where we used the one that had been beat up a little more on the assembly testing and launch operation side of things. And then as we got ready for sample return, it also got a lot of use.
Excellent. And thank you again for the question from our participant. And actually, I have another question. I think this one might be for Nicole. What is a question, and this might be one of our last questions. This comes from Harlem Renaissance High School in New York, and they're wondering, what is a question that you'd like to find the answer to, but humanity just might not be able to answer in the next century due to technological limits? That's a big question. Any thoughts on that, Nicole?
Oh, this is a really cool question. I think so. A lot of what we're really passionate about studying scientifically with these samples is understanding the processes in the early solar system, in our early solar system, but also solar systems like ours, both to see, what features can create planets like Earth, but the steps before that, steps really early on. And our solar systems like ours go through a protoplanetary disk phase, where the gas still is present with the rocky materials. And so we're starting to, and have been both with Hubble and with Webb, seeing sometimes incredible images of those protoplanetary disks, but mostly what we see is the gas. And so being able to know and see and understand what's happening with the rocky material inside of those protoplanetary disks, I think is a technical challenge that we'll keep studying. But right now, our best way of studying it is by having samples of asteroids, of these leftover materials from early solar systems, until we can more directly observe some that happening in another solar system in its early days, or at least early parts of its history.
Fascinating. You know, it makes me think the more we know, the more questions we can ask. And, you know, the questions we can ask really just help expand upon the exploration and discoveries we can make. So excellent, excellent questions, excellent answers. And as I look at my watch, we are about 15 minutes past the top of the hour. So as we bring things to a close, first of all, I want to thank everyone who joined us today, from our live participants to our archived participants, to our facilitators, including Rosina, Kim, Suzanne. We thank you for helping our folks on the line be able to participate in today's session. But I also want to thank our speakers, Christopher, Salvador, and Nicole. Thank you so much for sharing your passion, your wisdom, your excitement, and everything about the mission and curation challenges and celebrations with everyone on the line. And Nicole, do you have any closing remarks for our folks before we officially close?
Oh, thank you all for your curiosity. And I think what has gotten most of us here is passion and curiosity, as I hope you've really seen from our presentations. And it is a lot of what keeps us going, even through those challenging times that this team has overcome throughout the last several years. So thanks for joining and for being interested.
Great. Thank you, everyone. We look forward to connecting with you again sometime in the future. Have a great day.